Hello fellow problem solvers, so today we're going to be doing a problem from the 2004 IMO, problem number 6. I suggest you try this problem out for a minimum of an hour and a half, ideally 2.5 hours, but not more than 4 hours. If on the other hand you would like to go along with us, I suggest you take 15 to 30 minutes and put your first ideas out on paper. Try to push the problem further, get some ideas. So now, let's begin. So, this is the problem. We have a number that's alternating, has that its digits are either odd, even, odd, even, odd, even, odd, even, odd, even, or even, odd, even, odd, even, odd, even, odd. So they change their parities, like the consecutive digits in the decimal representation. And we must find all integers then, which have multiples which are alternating, i.e., and which divide some alternating number. Now for me, the first thing is, let me see which numbers definitely are not alternating. So the first number that comes to mind is, okay, what about 10? 10, okay, we can have. But what about 20? Well, 20, when is a number divisible by 20? Well, it's divisible by 20 when the last two digits are either 20, 40, 60, 80, or 00, which is impossible. So, no, so 20 does not divide any alternating number, which means every multiple of 20 also doesn't divide any alternating number. And now with this, I invite you to take another, say, 10 to 20 minutes and play around more with the problem. Do all the other numbers divide some alternating number? Or are there other numbers which do not divide any alternating number? So now for me, it's like, okay, let's see if it's 10 times t, where t is some odd number. So when will this happen? Well, okay, the last digit needs to be 0, and then the rest just needs to be divisible by t, right? Yeah. So let me just find, does every odd number divide, these alternating numbers? And now, in general, an alternating number ak minus 1, all the way till a1, a0, this is in fact, so it's 10 to the 0th times a0, 10 to the first times a1, so it's the sum till k from I equals 0, 10 to the k times, 10 to the I, times ai. And now, what would be maybe the simplest case to try out? Let's also say that t is not divisible by 5, just because there's 10s. I want to see like numbers which are relatively prime to 10. So now, maybe 5s aren't that problematic for if it's, but it can be a power of 5, and then that's an issue. Let me just try not divisible by 5 at all. So this t odd number, not divisible by 5. So now, what would be the simplest thing for me to try out? Well, for me it would be like 1, 0, 1, 0, 1, 0, 1, 0, 0, 1. It can end in a 1, say. Or, actually it would technically end in a 0, but we can say it ends in a 1. Because if you want 10 times t, you just multiply everything up by 10, and you have 10 times t. So, now with this number, what is its form? It's 10 to the, so there's how many digits? So this is going to be the 0th, the 1st, the 2nd. So even number, 2t. Actually 2 times some k. So it's going to be 10 to the 2k plus 10 to the 2k minus 2 plus all the way till 10 squared plus 1. So what is this? Well, if we write 10 squared is equal to x, this is 1 plus x squared plus all the way till x to the k, which is equal to x to the k minus 1 over x minus 1. And now with this, we have that this whole expression is 10 to the 2k minus 1 over 99. So it's 100 to the power of k minus 1 over 99. And we need to show that this number is divisible by any odd number. Now this number will, we can make this happen, just like make 100 to the phi of t minus 1, because t is relatively prime to 100, this will be divisible by t. And now the only question is, what if t has something in common with 99? But then we can just say t to the power of 100 times, let me figure this phi. What can we do with it? Well, I can just make it 100 of phi 99 squared times t minus 1. Now this whole number will be divisible by 99 squared times t, and so the whole number over 99 will be divisible by 99. Okay, 99 squared was an overkill, but it will be divisible by 99t. So we have all the odd numbers which have nothing in common with 5. So now from here, I invite you to pause for another 20 minutes and try to push the problem further. Here's the next step. So these are the numbers which work, these are the numbers which don't work. And which numbers are missing? Well, we want to make sure that we take care of these cases with tens, like numbers which have something in common with 10, carefully. So maybe the numbers which are missing are 5 to the power of alpha times t, where t and 5 is equal to 1, or maybe actually t and 10, where t is like an odd number. So that's a case we have. And I would say with that, we may be covering all the odd numbers, right? All the odd like this is all the odd numbers which are not divisible by 5, which actually have nothing in common with 5. And these are all the odd numbers which have something in common with 5. And then we have the even numbers, and there are a couple of even numbers at hand here. There are even numbers that are, these are even numbers that are done. So now what are the ones that we have remaining? I invite you actually to pause for 3 minutes and figure it out. Here it is. And it's this, 2 to the alpha times t, where t has nothing in common with 5. And I believe that this covers this, and this covers all the numbers, because these are the odds. These are the odds that have nothing in common with 5. These are the odds that have something in common with 5. That covers all the odds. These are the evens that have something in common with 2 and 5. These are the evens that have something in common with only 2 but nothing with 5. And these are the evens which have something in common with 2 times 2 and 5. So I think that covers all the numbers. Actually, a better way to say that is evens with something in common with 5, evens with nothing in common with 5, odds with nothing in common with 5, odds with something in common with 5, and those that don't work. So, which are the evens that have something in common with 2 times 2 and 5. So now what we need to do with this is to realize, okay, we have the odds. And I'll remind you the number, like we have every odd we can find a number. And let's say that number is A1 through, let's call it B1 through B2 all the way through some BK, such that t divides it. Well, then we can add a bunch of zeros here. And then we just need to find a number that 5 to the power of alpha divides and 2 to the power of alpha divides. That's alternating. And then we can like add the number of zeros that we need. This may be more actually, how difficult is this? Like, we just need to maybe figure out if we have any parity issues or not, but we can do that. And now that's a strategy. And I invite you here to pause and play around with this. Try to find these numbers for the next 10 to 20 minutes. So now here's the construction with 5 to the alpha times t. So what we have is 5 to the alpha divides one of these numbers. Okay, so that is what we need. We need 5 to the alpha to divide an alternating number of the form ak minus 1 all the way till a0. Now for 5, we have 5 divides 5. For 25, we have 25 divides, well, 25. Then 125 divides, well, again, 125. And now 625, well, we need another number. And here is where I actually, like, here's the thing what we need. We need to pick the first 4 digits to be divisible by 625. Because after that, every other number, if you think like the 5th digit, if the number is A, B, C, D, E, then what this is 10 to the power of 4 times A plus 10 to the power of 3 times B. And now you can see, like, no matter how you pick A, you will get the same remainder that you have with B, C, D, E. So now the question is, could we maybe how can we construct these numbers? Like n numbers for 5 to the n. And here I invite you to pause for 10 minutes, see if it reminds you of something potentially that you've done beforehand, or if you come up with any ideas. So for me, it's actually that I solved a problem similar to this from the United States Mathematical Olympiad. And the problem is that for every through that you can find an n-digit number with all odd digits such that 5 to the n divides it. and it has a similar idea to this one. So we can prove this inductively. Assume we've done this for 5 to the n, we found n digits, and now we look at what happens, like let's call this number n, let's call this number actually k. And now what happens when we append like a to the beginning of k? Well, that number we need to have, this is a times 10 to the n plus k, because k is an n-digit number. But what we know is that 5 to the n divides k, so let's k be equal to 5 to the n times l. So now we have, this is 5 to the n times l, i.e. we need 5 to the n plus 1 needs to divide 2 to the n times a plus l, and all of this times 5 to the n, which means what's enough for us is to have 2 to the n times a plus l to be divisible by 5. Like, this is what is enough for us. And here a is one of 1, 3, 5, 7, 9, or it has to be one of 0, 2, 4, 6, and 8. And now can you make sure that this will always, for one of these a, this number will be divisible by 5? And this is a common technique in number theory, somewhat common actually, that you have all the residues. Assume two numbers here for some two different a, two numbers are the same modulo 5, then you would have 2 to the n times a plus l. Mine is congruent to 2 to the n times b plus l mod 5, which means that 5 divides 2 to the n times a minus b. No two numbers here are divisible by 5. No two numbers here are divisible by 5, which is a contradiction. So at least, so all of them form all the residues of 5 for a 1 through 1, 3, 5, 7, 9, or 0, 2, 4, 6, 8, which means that we can find always an a. We can always add another a such that the number is divisible by 5 to the power of n. Now, do we need to be very careful with how many digits this number t, like this number that t divides, has? Well, the answer is no, not really. If we have 5 to the alpha, say we can have alpha digits, say this digit is odd, then how many digits do we need? Well, we start with 5. Well, we start with a 5, so we start with an odd, and we need to end with an even. So we just have, if alpha, that means alpha would be even here, but we can have 2 to the alpha plus 1, or 5 to the alpha, like one of the two we choose to make this whole thing divisible by 5 to the alpha, and then we append this t number, and we are done. And now with that, I invite you to pause for another 10-20 minutes and see if you can finish the case with 2 to the alpha times t and finish the problem. So here's the next case. So this is our final case, 2 to the alpha times t, and the same thing holds. We need numbers. We need the first alpha of them, actually, the first alpha of them, so from a alpha minus 1, a alpha minus 2, all the way till a0. This needs to be divisible by 2 to the alpha, where this number is alternating. Now, I tried applying the same induction and it didn't work out that well for me. So what I did, I needed to modify the induction. The reason I needed to modify it is because when you get 2 times 10 to the k, this number is no longer just like a residue modulo 2 to the 2k plus 1, but it's actually 0. I mean, it's 0, and you can't really do much. And then 4 times this is also 0. So again, you can't do much, and you have a problem. So for me, instead of going induction 1 by 1, I decided to let me try to do induction 2 by 2. So from n till n plus 2. And really, if we have for n plus 2, for our intents and purposes, it solves our problem. And now how do we do this? Well, I decided, like, okay, let's start with 32. And let's make this number not just divisible, so this is not divisible just by 2 to the power of 2, but it's divisible by 2 to the power of 4. Let me add 2, let me add something extra. And in general, if let's say I have, I have an even number of these digits, so ak minus 1 till ak minus 2, all the way till a0. I have this number is divisible by 2 to the 2k plus, say, 2. And now I want to add 2 more digits. Actually, I don't need plus 2, I need plus 1 in my calculations, but here it is. What happens when I add 2 digits, when I add a and b? Well, when I add a, b, a 2k minus 1, all the way till a0. this needs to be divisible by 2 to 2k plus 3, by sort of an inductive way of thinking about this. And here we have that b is even and a is odd. So what is this going to be equal to? Well, it's going to be equal to, call this n times 2 to 2k plus 1. This is going to be equal to a to the power of 10 to the power of what? 2k plus 1 plus b to the power of 10 to the 2k. And then this is going to be plus n times 2k plus 1. Now b is even, so b is of the form 2c. And now I have 2 to the 2k plus 1 times a times 5 to the 2k plus 1 plus c times 5 to the 2k plus n. And what do we need to complete our induction? Well, this whole number needs to be divisible by this, so we need this thing right here to be always divisible by 4, that we can always pick. So a is an element of what? It's an odd, so it's either 1, 3, 5, 7, 9, and c is one of 0, 1, 2, 3, 4. So now, what is this number modulo 4? So modulo 4, this number is congruent to a plus c, because this is 1, plus n mod 4. So we need to show that no matter what our n, we can choose an a and c such that this is divisible by 4. Now that isn't too difficult. We can just say let a always be 1, and c is going to be 0, 1, 2, 3, and we get all the residues like that. We get, if n is -1, we do 1, 0. If n is 2, we do 1, 1. If n is 4, we do 1, 3, and we are done in every single one of these cases. So now this sort of combination gives us 2 to the power of alpha times t for any odd t. And now I invite you to pause for another 20 minutes, put all of these ideas together and write up a solution, because that's what we're going to be doing next. So the first thing we do is we say that we shall prove that all n not divisible by 20 have an alternating multiple. So for 20 dividing n, we have n divides this number implies 20 divides the number, and that implies that 20 divides a1, a0, which implies that a0 is 0 and a1 is divisible by 2, which implies that this whole number is not alternating. And now we move on to our second claim, which is, so we first proved this, that for k and 10, 1, having just 1 in common, we have k divides an alternating number. And what we do is just set this. Look at this number, sets t to be equal to phi of 99k, and we show that this implies that k divides this number. So now with that, we also move on to our third claim, which implies that also 10 times k also divides a alternating number. And now with that, we move on to our third claim, which is, and so with that, we have that 5 to the alpha and 2 to the alpha divide alternating numbers. We first proved this for 5 to the alpha. We say we prove it by induction, assume this is the case, and then we show that we can always find 1 such that 5 to the alpha plus 1 divides it. And by induction, we have for all 5 to the power of alpha. And now we move on to the 2 to the power of alpha on the next page, which is, so now for the 2 to the power of alpha part, we just prove that we can choose 2k plus 1 of these such that this whole thing is true, and we prove it inductively. And now with that, we move on to our fourth and final claim, which is that 5 to the alpha times k, where k is not divisible by 2, and 2 to the alpha times l, where l is not divisible by 2, both divide an alternating number. And we prove this on the next page. So, in trying to write this up, I actually came across a pickle, meaning that we can't really just do this with all the knowledge we found so far. Because what we really need is for every single k, not just to divide xk, because we're going to be adding like this number 10 times 10 to the alpha times xk to c and this one to d, or the other way around, I don't remember. But the thing is, we can't just do this and expect the number to be divisible by k. So what we actually need is for every k that has like nothing in common with 2 and 5, we need to show that there's an alternating number which has what? Which has any remainder modulo k. Now, how do we do this? Well, for modulo 1, we already had like what? 100 to the phi of, phi of 99k. is congruent to 1 modulo k. And this gives us the this gave us like the 1 0 1 0 1 0 all the way till 1. And now can we maybe work with this and expand it? I invite you to take another 20 minutes and try to work with this and expand this problem. And here's the next step. So we have this thing right here. And what we need is we need to now be able to change the remainder. Make the remainder, instead of being 0, we need to make it 1, 2, and so on and so forth. So maybe now the question is like, first of all, is this the only number? And that answer is like no. If we just like write t as phi of 99k times some number, say m, this number is still divisible by k. But now, because like k divides, 100 to the power of phi 99k times m minus 1 over 99. So we're still good. This is still 0. And now, to this number, we can maybe switch some of the ones. And now I invite you to take 5 minutes and figure out which ones to switch. And the idea is, the major idea here is, instead of switching any single one of these ones, you switch the ones which are at this position. Because what happens when you add to this number 10 to the phi of 99k times some number j? What happens? Well, this is like adding something that's congruent to 1 modulo k. So you're switching it from it being congruent 0 mod k to it being congruent now 1 mod k. Now, will it stay alternating? Well, the thing is, what is this number like? Well, I mean, we can make it, it matters if it's even or odd. And here we have that this is to the 0th power, to the 2nd power, so we are good. We can always make j even, and we can always, this will be an even number actually, so we can always justify this. Now, this means that for a large enough m, we can always add, we can get all the residues modulo k. We can get 0 through k minus 1. And then with that, what we can do is take 3 minutes and figure out what we're going to do with that. Well, that will give us all the numbers of this form, and all of them will be, they will all be of that form, and they will all, like, with some, maybe you will add, you can make some of them freeze, like add this twice to some of them, and you will get all of those numbers. You'll get a set of numbers that are congruent to this. And now what happens is you will multiply all those numbers by 10 to the power of alpha, I believe. And when you do that, you will still get them the same, like all the residues modulo k. Why? Because if 10 to the power of alpha times a is congruent to 10 to the power of alpha times b modulo k, that implies k divides 10 to the alpha times a minus b. Because k and 10 have nothing in common, this means that a is equal to b. So you will have all the residues modulo k once you multiply all the numbers you get, meaning you add a bunch of zeros to the numbers at the beginning. And then with that, you can like figure out what's your residue when you have 2 to the alpha times k, or 5 to the alpha times k. And now you figure out the number that's divisible by 2 to the alpha, what is its residue modulo k, and then append the negative of that. Once you get all these things, you multiply them by 10 to the alpha, and you can pick one out. And the same with 5 to the alpha. Now let's actually write up that solution. So we first proved this lemma. There exists alternating number times 10 to the alpha is congruent to r modulo k for any r alpha, and k and 10 having only one in common. And we proved this as we said. We're going to be adding a bunch of 2's. These are all alternating numbers. And then 10 to the alpha, like all of these form all the residue class of mod k. And then all of these numbers also form the set of all the residues mod k, because if not, what we said before. And now we have this. And with this lemma, we apply it to our fourth and final claim like this. So the first step is this. We take alpha, that's odd, and beta, that's even, so that we have this, that the final digit here is going to be odd in both cases. And now what we do is we are appending these numbers, and we do this by the lemma, and this shows that k divides y plus d is alternating, k divides z plus c is alternating. And because we also have that, we have that because of these two things, we have the, what do we need for y? Because we're adding it to d, we need 5 to the alpha. We have 5 to the alpha divides y, which implies that 5 to the alpha divides y plus d, and 2 to the beta divides z plus c. And now both of these things with this imply that 5 to the alpha times k divides what? Y plus d. And 2 to the beta times k divides what? Z plus c. And with this we are done. And this shows that the only numbers which satisfy the problem relations are the numbers which are not divisible by 20. This solves our quite tricky problem, and as always, thanks for problem solving.